Hi everyone and welcome back. In our last video, we looked at how computers use algorithms to solve problems. We used the example of finding a specific name in a massive, totally scrambled book, and we saw that a classical computer has to check every single name one by one using a linear search. We covered how for massive databases this takes a really long time. But in computer science, how do we actually measure what a long time means? Well, the intuitive idea might be to first check how long a program takes to run and give an output. But there are two big problems with that. Firstly, if I run a really bad algorithm on $1 million supercomputer and you run a really efficient algorithm on an old laptop, my computer will probably finish first. But that doesn't necessarily mean my algorithm is better. It just means that my computer is faster. And secondly, running an algorithm is, in some sense, based on luck. If we go back to the example with names in a book, it's possible that we run the algorithm twice, but one time the name we're looking for is the first name in the book, and the next time the name we're looking for is the last name in the book. In one case, the algorithm will run in less than a millisecond, whereas for the other case, the algorithm could take years. To really understand computer science, we need a way to measure the efficiency of the algorithm itself, totally ignoring the hardware and the ordering of the values. To do that, we use something called Big O notation. Big O notation doesn't measure seconds or minutes. Instead, it measures steps. Specifically, it looks at how the number of steps grows as the problem gets bigger and bigger. In Big O notation, we use the letter capital N to represent the size of our problem. So if we're searching a book of names, N might be the total number of names in that book. Our goal is to figure out the relationship between N, which is the amount of data, and the worst case number of steps that the computer has to take in order to finish the job. Okay, let's do some examples now. Let's start off with the absolute best case scenario. Imagine I hand you a list of numbers, and all I ask you is the first number in the list the number 10? To answer that, you can open the book, look at the first number, and then say yes or no, which takes exactly one step. Regardless of whether the list has 10 billion numbers or just 10, you'll always be able to tell me whether the first number is 10 with just one step. In computer science, we write this as O of 1, which is called constant time. It's the most efficient type of algorithm, but unfortunately, most real-world problems can't be solved this easily. Now let's go back to our linear search from the last video, where we have to find a specific person in a completely unorganized list. If the list has 10 names, the absolute worst case scenario where our target is at the very end of the list, it'll take 10 steps. If the list has 1,000,000 names, the worst case scenario is we take 1,000,000 steps. Now, you should hopefully be seeing a pattern here. As the book gets bigger, the number of steps grows at the exact same rate. Because the number of steps is directly tied to n, we can write this as O of n, or linear time. And depending on how an algorithm is built, the number of steps can grow at entirely different rates. Some of the most common Big O functions you'll see are O of log of n, which we refer to as logarithmic time, O of n log n, or linearithmic time, O of n squared, which is quadratic time, O of 2 to the n, which is exponential time, and O of n factorial, which is n factorial time. The examples for these algorithms are usually a bit more complicated, but generally we aim to write algorithms which are not in exponential or factorial time, as they are very, very slow, even when n gets a little bit big. And this is the limitation that we've been building up to. For a lot of problems which can only be solved using these massive exponential or factorial algorithms, it's impossible to build computers which are fast enough to actually provide a solution. While we'll cover this more in depth during the quantum computing session, a large benefit of quantum computers is that they can actually reduce the time complexity themselves of a lot of algorithms, which makes it a lot easier to solve certain types of problems.